In the name of God, the compassionate, the merciful, engineering plasticity, chapter 3, yield criteria, part 4. Well, we have been talking about yield criteria for some times, and here, as you can see, this is the deviatoric plane. And sigma 1 prime, sigma 2 prime, and sigma 3 prime are the three axes, stress axes on the deviatoric plane. If you remember, we said that the deviatoric plane is perpendicular to the hydrostatic stress axis, and we could project everything from the three-dimensional stress space into the deviatoric plane. So sigma 1 prime, sigma 2 prime, and sigma 3 primes are in fact the projected views of the stress axis in the three-dimensional space. Now here we have a configuration like this. As you can see, I have drawn horizontal axis, we call it x-axis, and that point P in fact is the stress point. You know, in the previous slides, we had OP, which was the stress vector. Now this is the projected view on the deviatoric plane, OP. What are the components of this stress point? Along the axis, the stress axis, along this axis, OA is a sigma 2 prime. That's one component. The component along the sigma 3 prime is AB, and along the sigma 1 prime is PB. Therefore, that's how we reach to this point. Draw the magnitude of each component along each axis, and we get to the point of stress. Okay, as you can see, because this is a plane area, we could also have y-axis in here, y and x-axis. And we could find the relationship between x and y, and sigma 1 prime, 2 prime, 3 prime. And because we had scaled down sigma 1 to sigma 1 prime by this root 2 over 3, then we can relate x and y to sigma 1, sigma 2, and sigma 3. Also, we have shown here this stress vector OP, and we have the coordinates, Cartesian coordinates xy, and also the polar coordinates r and theta. So r sine theta, r cos theta, r and y and x. And we have considered a 60-degree area because these axes, sigma 1 prime, 2 prime, and 3 prime, are inclined to each other by 120 degrees. So because there is a symmetry of 60 degrees here, we just take a 60, because this is the sigma 1 axis, that's 120, that's 60. So that's 60. And the x-axis makes a 30 degree with each axis, with sigma 1 prime axis and sigma 2 prime axis. So you will later see that if we just consider a 30 degree area like that segment, that would be enough to cover all the areas in the stress space. And we will see that how it comes to cover it all. So in here we have this theta it changes from 0 to 30 degrees, and R shows the magnitude of the stress. Okay, so if we want to locate P, either we go by using sigma 1 prime, 2 prime, 3 prime, or we could use R sine theta or cos theta, and we will know where P is. Okay, and this is the previous yield function that we developed. Okay then, so sigma 1 prime in here, is PB. Okay, PB is sigma 1 prime and is root 2 over 3 times sigma 1. Similarly, sigma 2 prime is OA and is root 2 over 3 sigma 2, and also sigma 3 prime is equal to AB, which is root 2 over 3 sigma 3. Note that here we have these directions: uniaxial compression or tension and pure shear. Y is the yield strength in the uniaxial tension, and K is the yield in pure shear. So in the previous slide, we noticed that sigma 1 prime and sigma 2 prime on these two axes are given. So if we look at the stress vector OP, we could write OP squared in this plane, deviatoric plane. OP squared equal to OD squared plus DP squared, this triangle here. Okay, and then because OP we have designated as R in the polar coordinates, so we find a relationship between the polar coordinate and the Cartesian coordinates. Very simple relationship: R squared is equal to X squared Y squared, because OD is X and DP is Y. So R squared equal to X squared plus Y squared, and obviously X is equal to R cos theta and Y is equal to R sin theta, and therefore OD, which is X, could be written as sigma 2 prime cos 30. Sigma 2 prime is OA, in fact. OA cos 30 is that part, that length. Okay, so sigma 2 prime cos 30 minus sigma 1 prime cos 30. Now sigma 1 prime is this, PB, and that is 30, because this is perpendicular to that, parallel to that. PB is parallel to sigma 1 prime. So we could write here this PE is sigma 1 prime cos 30, and therefore this bit minus this length becomes equal to OD. Yes, so if we write this down in terms of this, root 2 over 3, and cos 30 is root 3 divided by 2, so we get the root 2 out of the multiplication of these numbers, and we get sigma 2 minus sigma 1 over root 2, which is also OD is R cos theta. Yes, OD is R cos theta. So you can see that we have found the relationship between X, the polar coordinates, and the stress components in the three-dimensional stress space. Okay then. Similarly, this Y, PD, also is equal to sigma 3 prime, which is this AB. Sigma 3 prime is AB, minus sigma 2 prime sin 30. Okay, because we want this PD. So if we subtract this length, minus sigma 2 sine 30 is this. It's this part. So whole AB minus this part, which is sigma 2 prime sine 30, and minus sigma 1 prime sine 30. That's sigma 1 prime minus BE as well. So AB minus BE and minus this part becomes this part, which is equal to PD. Okay, so PD is equal to, again, substitute for sigma 1 prime, 2 prime, and 3 prime. And we get this 2 sigma 3 minus sigma 2 minus sigma 1 over root 6 equal to r sine theta. Note that here we have find x and y, which are the coordinates of P. Also, we have found r cos theta, r sine theta, which are the coordinates of P. Note that theta is not 30. Theta changes from 0 to 30. Okay, this was the yield function that we had, and these x and y we obtained from previous slides. So we could write r squared equal to x squared plus y squared. We have these two. We substitute here, and therefore r squared is equal to that. This relationship is very similar to this relationship. Okay, r squared equal to 1 over root 3 sigma 1 minus 2 squared, sigma 2 minus 3 squared, sigma 3 minus 1 squared. Okay, so still note that this r is OP. Okay, OP. So if theta goes to 30, then we go to that. I will explain in a minute. So here, let's see, when the stress reaches the yield surface and the material yields, it means that if OP increases such that it reaches the yield surface, we are supposing that here is not the yield point yet, but if it increases such that it reaches the yield point, then supposing that is the yield point, then we had x and y from previous slide. Here we say that OP is equal to r and is equal to root 2 over 3y. What is this? This is the radius of the cylinder, okay, or circle. So we said if OP increases and reaches this value, then yields occurs. And note that here Y is the yield strength in uniaxial tension, and pure shear we have taken K as the yield. Okay, so in case of uniaxial tension, we have X equal to r cos 30, because we said theta can change between 0 and 30. If it becomes 30, then we have uniaxial tension. So that's uniaxial tension, and if we substitute this in here, we get y over root 2. And also coordinate y for when theta is 30 becomes y over root 6. Okay, note that this OP should be equal to that for yielding to occur, and for uniaxial tension, then theta is 30. So if we substitute this for r and 30 for theta, then we get y over root 2 for x and y over root 6 for y. So that's the coordinates of P when it yields. Okay, because this x and y are in general the general coordinates. Therefore, you can see that as OP increases in magnitude and reaches the yield surface, we have the coordinates become this. But these are the coordinates for when it has not reached the yield surface yet. Okay, it's just a state of stress in general. Also for pure shear is this one. OD is pure shear. Now, here we don't have any normal stresses. We just have shear stresses. So if we put for theta equal to 0, and that's the yield point, we put it here, then we get K equal to root 2 over 3 times Y. It's according to this criteria. And Y is equal to R sine 0 is equal to 0, so Y is 0. So that is OD. When it reaches the yield point in shear, which yield point in shear, we usually call it K. And this is the relationship between K and Y. Okay, now then, for experimental determination of yield criterion, it is convenient to introduce the load parameter mu defined as this. Now this is the paper by Load. If you can get it and read it, it would be very nice, but I think it would be maybe in German, I don't know. But I may get it for you and upload it to have a look at it. Now mu is minus root 3 tan 30. So where did he get this parameter? From dividing y by x. If we divide y by x and then times root 3, we get this. This is the numerator here, the numerator, and the denominator here we have the numerator of x. So it's y divided by x times root 3 times minus 1. We get this relationship, which is very interesting. You know, if you use this load parameter is tangent 30, tangent theta, and change between 0 and 30 due to symmetry of this axis, it's only needed to do the experiment for 30-degree zone. And because all other zones are just a repeat of this, you know, they are mirror images of this all over the place. So we call that load parameter root 3 times 30 negative, or we put these numbers here, okay, for sigma 3, sigma 2, sigma 1, and we get mu. And it is shown that to obtain the yield locus, it is only necessary to apply stresses for which theta covers the range from 0 to pi over 6 plus minus, and mu varies from minus 1 to plus, because that's minus. When we put pi over 6, we get plus. So minus 1 to plus 1, the parameter mu changes, and we get all the points necessary to draw the locus for the yield surface. Okay. So in here, if we put mu equal to 0, this numerator becomes equal to 0, and then we get sigma 3 equal to half sigma 1 plus sigma 2. Obviously mu equal to 0 is theta equal to 0, and we have a state of pure shear as shown here, and the stresses are denoted by this half sigma 1 minus sigma 2, sigma 2 minus sigma 1, and 0, plus a hydrostatic component sigma 1 plus sigma 2. If you see that if we add this hydrostatic component to the first term, we get sigma 1. If we add it to the second term, we get sigma 2, and sigma 3 obviously is 0. Okay, and that is for mu equal to 0. And also here, if we put mu equal to minus 1, we get sigma 2 equal to sigma 3, a state of uniaxial tension, which is this one, because theta is equal to 30, mu is equal to minus 1. And we get, if you put mu equal to minus 1, because here This minus goes with that, and then we get tan 30 because 1 over root 3 is tan 30. So that's correct. If you put mu equal to 1, we get theta equal to 30, and sigma 2 equals to sigma 3, and we get only sigma 1 prime. And the state of stress is equivalent to uniaxial tension, which is sigma 1 minus sigma 2, 0 and 0. Okay? And hydrostatic stress sigma 2, if we add this to that, we get sigma 1, 0 and 0. And